The reason there are cracks here is because this whole plate was, all of this was laid down flat in a shallow sea 300 million years ago. But you see that these limestone beds are bent. They go up as they go up to Dunangus, and they come down into this shallow, and then they go up. You see the ridge over there? So this whole plate, this whole island has been bent and broken. And as soon as you bend a dense, hard rock, it breaks. But it only breaks in small fractures. And these big fissures are caused by the rainwater coming in with the carbonic acid, dissolving it, and it widens. The water always seeks out the weakest point and goes along it. And so you see it comes along this fissure right here, which is the weak point, and then it intersected this one, and it took it that way. And then it died out there, and you can follow that same fissure pattern down to the ocean.
Oh.
So this is where we saw something unusual in this massive gray terrain of limestone. You feel this, it's squishy and slimy, and you feel it push hard enough, and you feel the clay in it. Well, there's very little clay, if any clay, in limestone. So this is being created right here in this little depression, a little microenvironment that is creating a soil. The other thing we see on this terrain is this gray limestone has these boulders on the top that are not limestone. And as we go along, we see several different kinds. And these rocks are called erratics. And the pink one over there is sandstone. And this large one right here is a large boulder of granite. Well, there isn't any granite on this island. There is granite on the mainland of Ireland. So how did this block of granite get here? Well, 18,000 years ago, the glacial periods were ending, and the glaciers that had swept through all of Europe and Ireland and out to the ocean were melting. Sea level was 300 feet lower than it is today. And as the ice melted, then these rocks were dropped out as the ice melted. It's igneous, and it was created subterraneanly. As it cooled, these minerals were growing, and so it's totally different than a sedimentary rock of limestone. So this rock came from the mainland of Ireland and was deposited when the glaciers retreated and melted. And if you look, this is a hand lens, and you focus it like this, and you can see in the fresh areas, you can see where, see the different grains in there. They're different minerals. There's quartz, feldspar, plagioclase, not too much mica. But so this is a granite.
So many grains in this.
So many grains, that's right. And here's another piece of an erratic. And this one was a gray sandstone. And you can see, bring it closer there. There you go. Yep. And you can see how fine grained that material is. And Jen, if you would hand me that rock behind you.
This one here?
Yes. It's still another type of rock. This is a coarser grained sandstone. And you can look in it and see the many different rock fragments and minerals that were weathered from a granite and deposited in a sedimentary rock. And this is another type of sandstone.
Thank you.
That is in this terrain that is all limestone. So that's where these erratics came from. And it's part of the story of the history of glaciers that really was not understood until a theory of the Ice Age was published in 1849. They were still assuming or using a biblical origin of the Great Flood for these erratics until it was clearly seen from the pattern of deposition that they weren't laid down by water. They dropped out of glaciers. So we'll walk on down the field here. We'll walk across here and look at some more. Now we'll go over and look at some more of this terrain, see what other features we can define. More erratics here. Now, you notice this fracture, these crevices in the limestone, and these are naturally occurring fractures. And if you look at the walls that are man-made, they're made of this rectangular shaped limestone that was created by natural fractures. And you see that at the surface, these fractures, which in the subsurface below this, the rock that's still buried, the fractures are microscopic. But they come to the surface, and rainwater mixed with CO2 in the atmosphere creates carbonic acid, and that acid dissolves the limestone. And that's why you have these irregular surfaces on the limestone. That's not a depositional feature. That's from chemical erosion of the calcium carbonate. And some layers are more resistant than others, and so therefore you get this very sharp and unusual erosional pattern. It's not the normal surface of the rock.
Same here.
Yeah, it's a chemical reaction of the rainwater with carbonic acid and the limestone. And you see the fractures are horizontal. They occur in an orthogonal pattern. They have right angles. And you see the wall rock that's man-made. Well, they picked up those rocks and so they made a nice naturally occurring building block. And we see that all over the island. And something that we've learned on this trip with, the Inishmore is only 27 square miles.
Oh.
The whole, but it has 7,000 miles of walls, man-made.
Wow.
One stone at a time.
Those take ages.
Take a long time. So we'll come down here and look at some other features. Be careful on these. Some of them get quite sharp. As we make our way across this field, we'll go to the wormhole, Pol Nebesh. And something we can see from here. And don't step where the grass is, because sometimes they're just holes. Something, if you look on the far cliff, just below Dunangus, the fortress, that black layer you see is shale. Now it was laid down in the ocean. It wasn't deposited like the little microenvironment we saw there. This was laid down in a very oxygen-deprived ocean, and that's why all the organic material remains, and it's black shale. And as soon as you start putting shale, which is a clay mineral made up of clay minerals, into a clear ocean, the deposition stops, and so you get 100% shale. And you'll see that those layers can actually be correlated to this same rock, the same Mississippian age rock over in North America. So at one time these continents were together, and you can map these same units into America and Canada.
Is that Pangea?
Pangea, and Gondwanaland, and when the Pangea was when it was all one, and then it wasn't until the 1970s when the theory of plate tectonics was accepted as a fact. Early in the 1900s, Dr. Wagner had developed something called continental drift, and he did that just by taking the continent, maps of the continent, and putting them together like a puzzle. And they said, well, they all fit. You can look at Africa and South America and just put the maps together and they fit. Well, they actually did spread from a mid-ocean ridge that is still moving today, and the plates are still all moving around the surface of the Earth.
Do they move by much each year? Or?
Not well. It depends. Some of the plates in the Caribbean move a centimeter a year, centimeter, which may not seem like much, but is very rapid movement in geologic time. Australia moves quite rapidly, and Antarctica is staying pretty stable down there at the South Pole. North America is fairly stable boundary. However, there's something called the Ring of Fire that goes all around the Pacific Ocean, where those are all very active plates, and volcanoes occur there. And in the Caribbean, you see these island arcs that were created by volcanoes, and that's where two plates collide. So that's the plate tectonics. We can map the movement now using satellite geodetic surveys. So we came down from the ridge just above the wall and down into this opening. We're looking at this naturally occurring ridge, and it's, believe it or not, would be considered a beach ridge. Now, where you went swimming at Kildaney, the sand, little very fine-grained sand,
Yeah.
well, that's there because it's in a certain energy environment. The waves are gentle enough that it just moves sand. Well, this beach ridge was created during the storm of 2013, and 2014, January, February 2014. And so those are deposited by wave action, just as the sand grains are. So you have to just think about how much force the waves have to move boulders the size of automobiles into a beach ridge. And when I was here in 2013, that was not there. That was an open area. There actually was a ramp down to a kayak ramp that fishermen used to use, and now it's all covered with these giant boulders. So the force of those storms is tremendous. You had those storms in Ireland, you remember?
Yeah.
Yeah.
Were the waves really, really big then to be able to throw them the whole way over?
Right.
So they just brought them all into here.
Mm-hmm. So as these cliffs eventually erode and drop large blocks of limestone into the ocean, well, the waves eventually rework even something the size of a car or a refrigerator. It takes a lot of force to do that.
Yeah.
Okay, well, we'll go on to Polnadesh.
Oh.